All right, welcome to CPI's USACO February workshop. Um, for which question do you think was the easiest? I'm hearing a lot of people in chat saying silver palm 2 and gold palm 1. Well, today we'll be going over all bronze and silver solutions in that order. And we have a very talented team of CPI instructors who are going to be teaching this. Approximately, we'll be finishing bronze at around 4:40. And so it'll probably take about an hour. So expect the workshop to last until around 5:30 or so. So yeah, without further ado, um, I'll hand it off to Rohan.
Um, Hello everyone. So I'll be going over bronze 1 and bronze 2. So we'll be starting with bronze 1. And the problem asks, Bessie's a hungry cow. Each day for dinner, if there's a hay bale in the barn, she will eat one hay bale. Farmer John does not want Bessie to starve. So some days he sends a delivery of hay bales, which will arrive in the morning before dinner. In particular, on day DI, Farmer John sends a delivery of BI hay bales. So the constraints are the values are both one of the DI is between 1 and 10 to 14th, and BI is between 1 and 10 to the 9th. So we're trying to find the total number of hay bales Bessie eats in the first 2 days. And T is also between 1 and 10 to 14, and N is between 1 and 10 to the 5th. So it's given that the list DI is already sorted. So like the days that the hay bales are delivered are in increasing order. And we're trying to figure out the number of hay bales Bessie eats during the first 2 days. So if we just like loop over each of the T days, we can check if Bessie eats a hay bale on that day. So if there's a delivery on that date, then we can add to the number of hay bales left. And if there isn't, then we just check if the number of hay bales is greater than 0. And if it is, we can decrement it by 1 and add 1 to our answer. So this runs in like O of t with O of t space complexity if you're using an array to store which days a delivery comes on. Or you can do an O of t log t using a map. But both of these are too slow to pass, as t can be up to 10 to the 14th, and USACO usually can only support up to like 3 times 10 to the power of 8 operations per second. So we need to make our solution faster. And the first question I'm going to ask is, what happens to the number of hay bales in the days between 2 deliveries? And the answer to this question is, every day it goes down 1 if there's a hay bale left, or if there are no hay bales left, then Bessie doesn't eat anything. And this happens every day until a new delivery. So essentially, the number of hay bales goes down until one of the two things happens. No hay bales are left, or there's a new delivery of hay bales. So if there are B hay bales and D days until the next delivery, the number of hay bales Bessie eats is simply the amount of time until one of these events occurs. So the first event occurs at the minimum of B and D, because if Bessie just ate one hay bale every day with no limit to when she would stop, then it would take B days to eat all the hay bales. But since if a delivery is coming in D days and D is less than B, then there would be a new delivery before Bessie finishes all the current hay bales. So the number of hay bales Bessie eats before the second delivery is the minimum of B and D. And doing this, we can add the minimum B or D to our answer, which is the number of hay bales Bessie eats in total, and also decrement this from the total number of hay bales that we currently have. And then when we get to the next delivery, we can add the number of hay bales that delivery sends to our answer, to the number of current hay bales, and repeat this process. So for a full solution, we create 2 variables, hay bales and answer. And for each delivery, we add the number of hay bales it sends to the variable hay bales. And this is basically storing the current number of hay bales. And then we find the number of days until the next delivery. So if there's like 5 days until the next delivery, and we have 3 hay bales, then Bessie's gonna eat 3 hay bales, and two of the days she won't have anything to eat. So the minimum of the number of hay bales and the number of days will be the amount of hay bales eaten. So we can decrement the number of current hay bales by this much and add the same amount to our variable answer. So essentially what we're doing is if we have a delivery here, so we get some like hay bales, and there's a delivery on like day D of 0, and then there's a span of days, and there's another delivery at day D1. We're just trying to find the number of hay bales Bessie eats between these two deliveries. So for each day, our code takes like one operation to run. So our runtime will be O of n because we process the deliveries at we process each delivery once, and this speeds up our solution from O of t to O of n, and this should run in time because n is less than 1 to the 5th, well 10 to the 5th, and that will run in a second or two. So here's my code for the problem. Okay, so the first thing I did this in C++, and you can convert this to Java or whatever other programming language you use on USACO. So for starters, I just did define int as long because the values are pretty big and can be up to 10 to the 14th. So I didn't want to worry about using LL every time or using int. So I just defined that as long. And then I took the input of the number of deliveries and the number of total days. So here I did some common trick, which is on the last delivery, there isn't a next delivery. So we have to check the number of days until the ending of like the problem statement. And it said the problem, we're only trying to figure out the number of hay bales Bessie eats for the first 2 days. And to like implement this trick, instead of making the day array size n, we make it of size n plus 1. And with this, we can store dn as t plus 1. Then we don't have to worry about edge cases such as when we reach the end of the array, we won't have to like worry about checking if there's another element after that in the array. So I take the input of the number of days in hay bales in the array, and I keep 2 variables. So variable ans represents our answer, and variable b represents the number of hay bales we have. So for each of the deliveries, we first add the number of hay bales that we get, and we do b plus equals bales I. And now we compute the minimum which is equal to the number of hay bales Bessie eats between this delivery and the next delivery. So this will be minimum of b and di plus 1 minus di, because that's the number of days until the next delivery. And then we increment the answer by that much, and we decrement the number of hay bales by the same amount. So, and then at the end, we just print the answer. So that's how you do rounds P1. Does anyone have any questions? All right. I guess we can move on to bronze 2. I think this one, in my opinion, this one was the hardest bronze problem on this contest. So let's go over it. So in this one, Bessie is stamp painting that she would like to create. So Farmer John gave her a single K by K stamp to do this and an empty N by N canvas. Bessie can repeatedly rotate the stamp clockwise by 90 degrees and stamp anywhere on the grid as long as the stamp is entirely inside the grid. Formally, to stamp, Bessie chooses integers ij such that I is in the range 1 to n minus k plus 1 inclusive, and similarly, j is in the range 1 to n minus k plus 1 inclusive. And for each I prime j prime such that I prime j prime are between 1 and k inclusive, the canvas cell I plus I prime minus 1, j plus j prime minus 1 is painted black if the stamp has ink at I prime j prime. So Bessie can rotate the stamp at any time between stampings. And once a canvas cell is painted black, it remains black. So this is probably one of the most key parts of the problem. So I'll just like underline this. And this is what motivates most of the solution. And you have key test cases, so you want to answer this question, all of them. Okay, so first let's like debrief the problem. So essentially we're given an n by n grid of zeros. So let's just say n is equal to 3. And we have a stamp of size k by k. And in this case, let's let k equals 2. So, and the stamp be 1, 0, 0, 0. Okay, so what we do know is that we can rotate the stamp anytime between stampings. So essentially, instead of thinking that we have one stamp that can be rotated, let's just think of this as instead of having one stamp that can be rotated as many times as you want, we'll have 4 stamps that can be used at any time. So rotate this one, 0, 1, 0, 0, and so on. So there's 2 other stamps that we have. And we have 4 stamps, and we would like to create a painting. So the key part of this problem is that once a canvas cell is painted black, it remains black. So let's just say we're given this, and the final grid we want is, I don't know, 1, 1, 0, 0, 0, 1, 1, 0, 1. So if we have something like this, and let's just say we wanted we're gonna put a stamp on this subgrid right here, and we choose a stamp 0, 1, 0, 0. So this is the original stamp rotated 90 degrees counterclockwise. And if we stamp with this stamp, then in our empty grid, this value in the middle right here becomes 1. And since it became black, it remains black, and we can't change this. And this is bad because if this is black forever and we can't change this, then this means we can never possibly actually get the real grid that we want. So this is unoptimal, and this leads us to the finding that if we're gonna stamp a subgrid of size k times k, then we only do it if all the black cells that we're stamping are actually black cells on the final grid. Because if they weren't black cells on the final grid, then that would be bad. So we go move on, and I've got to clear my annotations. Sorry. Okay, so what are the possible places to place a stamp? Well, it was kind of given to us in the problem statement, but there's n minus k plus 1 squared subgrids of size k times k. And also another thing to note is that if we leave a black cell that was a cell that was black in the final grid, and we left it white in the current stamping, it isn't that big of a deal because we can always come back to it later. And in fact, we can kind of prove this to ourselves. Is like if we have a 0 here, and let's just say the answer to the problem was yes. So for one of the test case, the answer is yes. And we stamped, like the stamp that was used to cover this one in the answer to this problem, which was yes, was like it stamped this part of the grid. And let's just say we applied a stamp that touched this and left it white. So you stamp like this, and it was still white. Then we can always come back later and stamp it again to make this 1. So if we take another stamp, but this stamp has a black, like it has ink at this coordinate, then you want to color, then it gets colored black as we want. So if a cell is black when we're painting it, then it must be black in the final grid. But this is vice versa, because if it was white, then it doesn't matter, and we can come back to it later. And this leads us into the solution of the problem. Is if the black cells in the stamp are a subset of the black cells that we want in the actual grid, then we use a stamp. And the reason why this works is it's kind of like a greedy approach, right? If we can use a stamp, there's no harm in using it. Like the answer is preserved. So if we use a stamp and the answer is no, then it still stays no, because there must be some black cell that we were unable to paint even after using the stamp. And similarly, if the answer is yes, then there's always some like sequence of stamps that gets us to this scenario. And the rest of the problem, which I think is the hardest part, is actually simulating this and checking if each k by k subgrid to check if we should stamp it or not. And at the end, if the final empty grid is equal to the one that we want, then we can say yes, otherwise no. For the comment, I think you can since this is like O n to the 4, you can probably do this for like up to 100, but I don't think there's a faster solution. There might be a way to optimize checking a subgrid, but to like reduce it to n to the third, but like I don't think it can be done for like 1000 or whatever. So here's my solution, and this one's kind of long because this problem is just like not very gentle in terms of like how easy it is to implement. And so I first start off with a bit of definitions just to make the code like easier to write. So I just define parent as pi, pb as pushback, vi as vector int, mp as make pair, vvi as vector int. So basically a two-dimensional vector, f as first, s as second, and vector of pairs as vpi. So the first part of my code is just like a function to rotate the stamp, the original stamp. And essentially what it does is we first like find the size of the stamp, which is using matrix.size. Then for each of like the indices where the y coordinate is greater than or equal to x coordinate, we swap it with the respective thing in the like if you flip it around the center, so ij goes to ji, you swap it. But the problem with this is the elements in the first half get swapped incorrectly. So to account for this, we loop through this again, but we only loop the first half. And this time, instead of swapping ij with ji, we swap ji with n minus j minus 1 I. And this is a valid, this is how we rotate the stamp. So this is like the first step, because we want to, instead of thinking about it as we can rotate a stamp as many times, we want to think about this in a way that we have 4 different stamps, and we want to figure out if we can get the original grid with using these stamps. So the first thing that we do is we take the input of the actual grid. And what I did is I made a two-dimensional vector grid, and I took the input. So if the ink was black in that in the final grid, then I made the value 1. Otherwise, I made 0. So you can use booleans for this, integers. You can use characters, whatever works. I just felt integers was the easiest to work with. Then I took the input of the actual stamp, and I did a similar thing where I did like if there's ink there, then it's 1, and if there's no ink, it's 0. So here I use the rotate function 3 times to find all 4 possible stamps. So I first rotated the original stamp 90 degrees, then I rotated stamp 2 90 degrees to get stamp 3, and similarly to get stamp 4, I rotated stamp 3 90 degrees. And so the next step, it's actually not necessary, but I just did it to make the code a bit easier to work with, is instead of storing the entire stamp, I just stored the indices of the inks. So this is a vector of pairs, and I went through each cell in the k by k subgrid, or not k by k subgrid, just a k by k stamp. And if there was ink there, which is represented by if stamp ij, then I added it to the vector of pairs to like indicate that there's a stamp there, there's ink there, and when we stamp, it'll be black. So now we start off with like this is the actual stamp that we can create. And so first of all, we loop over all by k subgrids. So as they describe in the problem for us, is that the indices I and j are between 0 and n minus k inclusive. So yeah, and then so now we have a stamp which is like from ij, and then it like goes up k to the right, and then k to the k up. So this is like with the subgrid that we're checking. And this is also just for implementation to make it easier purposes. Now, instead of storing like the actual k by k subgrid, I just made a vector of bools, which checked if like each cell is black or not. So it's true if it's black, and if it's false if it's not black. And this is what this part of the code did. Oops, I cannot draw lines. It just checks if that location is black or not, and it stores it in the vector of bools. So now we check each of the 4 stamps. So this actually doesn't look, it's not as bad as it looks. Essentially, I just wrote this code once for the first stamp, and I copy pasted it 4 times to check all other 3 stamps. So what we do is we create a bool, which is the checker. We make it true originally. And for each element in the stamp, so this is the vectors of PIs we created, so this stuff. For each element in that vector of pairs, if the black in this index corresponding to this is if it's not black, then we make our checker false, because that means there's some black cell that we're stamping that's not supposed to be black, and this is irreversible. So we want to remove. We don't want to do this anymore. And if the checker is still true at the end, then we make in our final subgrid, which is act, we make each of the indices 1, which represents a black cell. So now I copy pasted this 4 times to do this for all the 4 stamps, and then at the end of our code, you just check if the final grid is equal to the grid that we can actually get. If it is, then we say yes, and if it's not, then we say no. And then this part of the code is just to handle the fact that there's more than one test case. So I took an input of number of test cases, and then while t minus minus, which just simulates all the test cases, I use the solve function to do everything for us. So are there any questions about this? Okay, if not, then I'll hand it off to Aditya for problem 3.
Hey guys, I'm Aditya, and I'll be presenting problem number 3. Can you guys hear me all right? Okay, great. So let's start with just what was question number 3 asking. So for question number 3, we had Bessie. She had a plan for N days for when she was going to watch Mulu. So basically, she had that she was going to watch Mulu on the 2nd day, the 5th day, whatever. And there's a cost for this Mulu subscription that she needed to pay for. It costs D plus K Moonies to subscribe to Mulu for D consecutive days. So you have to pay this base fee of K, plus for every day you have it, you pay $1 for that day, or 1 Moonie for that day. And given this, we have to figure out the minimum amount of Moonies that Bessie needs to pay to like complete all the days that she plans to watch it for. So the best way I like to tackle these type of problems is let's work through the test cases and see what our thought process is when we're solving it. And then the computer is probably going to have a similar thought process. So let's take a look at this first test case. So here we're given that she has 2 days that she wants to watch it for, and K equals 4. Okay, so the first day that Bessie's going to watch Mulu, that's going to be on day number 7. So there's no point on buying a subscription before that, but because she doesn't need to, there's no use for it. And since we're trying to minimize the cost, we won't buy that. So she buys it on day number 7. So it costs her $4 because that's the K, plus $1 for the 7th day. So that's $5. Now, the question is, now she wants to watch on the 9th day. Should she keep her subscription, or should she end her subscription and then rebuy it after the 9th day? And that sort of is the logic that we have to sort of solve here. And the simple answer is maybe we should just pick the one that's cheaper. Because if we keep the thing for 2 days, if we keep the subscription for 2 more days, we would pay for the 8th day when we're not using it. So that's a waste of a Moonie. And then we would pay for it on the 9th day, which would be 7. Or we could drop it after the 7th day and then rebuy it on the 9th day, which would again cost us 5. So that would cost us 10 in that case. So in this case, it's better to just keep the subscription the whole time. Okay, let's look at the other test case. So for this test case, we have n equals 2 and k equals 3. What this tells us is that on day number 1, we need a subscription. So once again, it's going to cost us $4. And now either we can keep the subscription for like the remaining days that we have. So we would need it for the second day all the way to the 10th day inclusive. So that would be 9 more days. That would cost us 13. But in this case, since the 10th day is so far away and K is low, we can get rid of the subscription and then rebuy it on the 10th day. So we would pay $3 as the base fee plus $1 for the 10th day, or 1 Mooney, which is 8. Okay, so now that we've solved these test cases, we have a good idea of how the problem works. And it seems that the intuition is on each day, try to pick the cheaper option, right? Either keep your subscription if it's cheaper, otherwise get rid of it immediately. We don't need to consider cases like let's get rid of it on the 3rd day, right? In the second test case, because that's not optimal. It's never going to be optimal to keep it on unnecessary days when you're paying extra money for each extra day. So let's look at the intended solution, or the solution that I came up with. So we consider the ith day that Bessie decides to watch Mulu, right? So whatever the ith day in her list is, if she needs a membership to watch Mulu on this day, because I mean, she can't watch Mulu without it, right? So what we have to look at is the next element in the list, whichever day it is. It might not be the next day exactly. It's probably going to be a few more days down the line. She can either keep the membership for all the days in between, or she can immediately get rid of it right after the ith day and then rebuy it when she needs it the next time. Like we just talked about earlier, it's not optimal to do anything else. So each time we can just say that she's going to go with a cheaper option. And the way we can find the cheaper option is compare both of these options, and whichever one is cheaper, go with that. And we can do this for each of the n days that she wants to watch Mulu and then sum our answer. So this approach gives us an O of n answer because we are only looking at the n items that she has in her list. And if you remember, the bounds on n are less than 10 to the 5. So this is going to run in time. Let's look at the implementation. All right, so first, Rohan talked a bit about this, but you set the vector size to n+1, so that way there's no problems with the edge cases. For example, here we're assuming that she has it on the ith day, and then we're looking at the next day, right? So we don't want any problems with that. And then what is another thing that we have to do to make sure there's no problem with the first case is that if you remember, in the general case, we look at the ith day and then compare it to the I plus first day, right? But in the first day, there is no day before that. So we just assume that's like negative infinity. And the point of this is it's trying to show that it's always optimal to buy the subscription on the first day, which makes sense because there's no other choice to not buy the subscription on the first day in Bessie's list. Okay, so we set our answer variable, we read in our data, and this is like where the code happens. So you can see that the actual logic behind the code is it just comes down to one line of code. And the idea is for each of the n days, check if it's cheaper to get rid of the subscription. And if you got rid of the subscription, you wouldn't pay anything for the days in between. You would just pay K for the base fee plus 1 for the ith day that you're on, $1 for the, or 1 Mooney for the day, for the cost of that day. Or if you keep your subscription, you don't need to pay the K base fee, but you need to pay for all the days in between and the end. So if it's a 5th and the 8th day, you would also be paying. So you would be paying for the 6th, 7th, and 8th day. We don't include the 5th day, so it's important to not be off by like 1 up or 1 down. We don't include the first day, the 5th day, because we've already counted that before. So simply, we can just compute answer is always going to be the minimum of these two options, and then we sum up our answer and get this. One comment I would make is make sure you pay attention to the fact that the answer, it's a 64-bit type answer, so we can just define our int as int 64. That way we don't have to worry about this, but you just change what the main statement's returning. All right, we can quickly check cases. So let's go build and run. And we can see the first case works. And the other one is 2, 3, 1, and 10. And that one should give us 8. Yep. All right. Any questions about that problem? Yeah, I do see someone saying that in the chat. It was the easiest question. I felt that too, because the actual logic, unlike number 2, it just came down to one line instead of having to set up a lot of functions. So once you see that trick that each time just pick the cheaper option, you're good for the problem. Yeah, this is the code blocks ID. If there's no other questions, we'll take a 5-minute break between the bronze contest and the silver contest, and then we'll be back with the silver solutions. Thank you, guys.
Yeah, I just want to say this real quick. If you're here for the bronze solutions, then we highly recommend that you also stay for the silver solutions, because there's a lot that you could gain from that. But yeah, other than that, we'll see you in 5 minutes. All right, cool. So now we'll be studying the silver problems. So I'll hand off to Albert to start off with silver problem 1.
All right, hello. I can see my screen. Oh my God, it was just working. Okay, now I'm screen sharing, finally. Okay, so for this bakery problem, we have n orders. TC is the time to bake a cookie, and then TM is the time to bake a muffin. And then basically we have AI cookies and BI muffins and a CI time limit for each order. We want to spend $1 to decrease TC or TM by 1. And you want to find the least amount of money such that all orders are satisfied, remembering that money goes to decreasing the amount of time made. So there is some amount of money needed in order to get all the orders satisfied. So let's do binary search on the amount of money we need, basically. So how much will we split between the cookies and muffins? So notice that if we cannot get like if no split exists for for X dollars, then no split can exist for X minus $1. I think this is pretty self-evident because assuming there is no A or B that satisfies both the cookie and muffin constraints in tandem, then reducing the amount of money we're spending is not going to help anything. So why did it just slip over there? So no, oh my God. If no splits exist for X dollars, then no splits exist for X minus $1. So how will we split between cookies and muffins? So this requires, there are 2 ways. So first, the motivation. So we have time. We basically can split between like dropping all of our time on cookies or all of our time on muffins. And if we do so, like there is a point where like the amount of money that we will be spending, the amount of time that we will be spending will start to increase. If we were to substitute more cookies for muffins or more muffins for cookies. So this sort of motivates like a unimodal graph like we see over here, where essentially things are first decreasing and then, well, we have a hard limit down here. So it's going to just stay at the hard limit and then it's going to eventually increase over that. If we increase the amount of time for, there is like a more rigorous proof for this, but I think that just looking at the basics over here is all that we need to do. If we increase the amount of time for a cookie, we can decrease for each cookie, we can then decrease the amount of time for the same muffins. So yeah, this is basically what we're saying here. So we have this progression in the graph, and there are two ways that we can deal with this because binary search is not enough for this case. So the first way is using something called ternary search. I don't think that this is ever going to be fair game on a silver contest, but you can like look it up. I don't think I will be going over ternary search, except that it is a solution that allows you to calculate like things that are unimodal, as in they like decrease and then they stay the same or increase, or you like increase, stay the same, then decrease or something. So you can solve things like this with ternary search. The better way to do this is with two passes of binary search. So the first way is you binary search over the amount of money needed to reduce TC to satisfy everything with AI greater than BI. So here we're either bottlenecked by cookies or by muffins. In the cases where AI is greater, then cookies are the bottleneck. And in all other cases, muffins are the bottleneck. So for our first pass, we want to binary search over the amount of money needed to reduce the time to make a cookie such that everything here is satisfied. And this would take a certain time C. And then we can do the same thing for all cases where muffins are better. And then we can use a time M. Doesn't ternary search. Honestly, I kind of forgot. It's been a while. But anyways, that's not really the solution that was intended, I believe. But I know people who have tried it and it worked. So ternary search works. You just need to like, if that's the case, you might just need to modify it a little bit. I honestly did not look at it that way. Binary search over amount of money needed to reduce the time to make a muffin, and then just such that like everything with AI less than BI satisfied. So this would give us 2 times C and M. We can basically just add the two because we would want to both reduce the amount of the time needed for cookies and the time needed for muffins. And then this would give us like C plus M is less than or equal to X, where X is the total amount of money that we're binary searching over here. So if this returns true, then we set the upper bound on X, otherwise we set the lower bound. So are there any questions? No questions on this problem, then I will hand it on to the next person.
Okay, so over to you. Okay, so for this problem, Farmer John has 5 gardens, and for each garden, there's a point that a cow will get to, namely X, Y, and T. So a cow can get to point X, Y at time T, and there are n cows, and n cows are trying to prove themselves innocent by saying they are at some point X, Y at time T. So the important part about this problem is here it says a cow can be determined innocent if it's impossible for her to have traveled between all the grazings and her alibi, and cow can travel 1 unit distance at a time. So a really common mistake about this problem is that a lot of people assume that a cow can only move parallel to the x and y axis, but the problem just doesn't say that. The cow can move literally in any direction. So this will be useful when determining if we use Euclidean distance and Manhattan distance later on. And this sentence in the input is really important because this basically guarantees that if we check 1 point, if we fix 1 point, if we know a cow is going to get to 1 point, it's able to get to all the other points in the time constraint. So what this also means is the time difference between 2 points is guaranteed to be less than a distance difference, since basically a cow can get to 1 point to another if the time difference is less than the distance difference. So let's rephrase this problem without the alibis. For each cow, if a cow was actually at the point specified, so if the cow was actually at their alibi point at the time they said they were, if a cow cannot get from a grazing to her proposed point, or cannot get from the alibi to a grazing within the time constraint, and she is innocent. So I'm going to rephrase that again. In other words, we need to check in a grazing that the point with the maximum time that is less than the time in the alibi. We need to check this point because basically you are going to move from this point to your alibi because you're essentially inserting a point in your grazing, and you want to be able to make sure you can get from the point in your grazing to the point in your alibi. And of course, we need to check the point with the minimum time that is greater than this time in the alibi. We need to check this because we have to move back into the grazing path. These are the only 2 points we need to check because all the other points have their time fixed, and we couldn't possibly reach these points in different order by time. And if you remember, in the input constraint, it says that a cow can move, it's guaranteed to be able to move to all the grazings in the time constraint. So again, a cow is able to get from 1 point to another if and only if the Euclidean distance between the points is less or equal than the time difference. All right, now let's do an example. So consider a cow with alibi at point 2020, which is the black dot at time equals 20. So first, let's check the point that it will move off to the grazing. So let's first check the green point in the grazing, which specifies it will reach it at t equals 50. So here we first check the distance from 2020 to 050 using the Euclidean distance formula, which is basically, if you didn't know, the difference in x coordinate squared plus the difference in y coordinate squared all over square root, and that equals 36.6. Now, since 36.6 is greater than the time difference, now cow is already not able to reach the time in this point in the grazing, which also means that the cow must reach it after it commits the crime, which disproves the cow's innocence already. Now, if hypothetically, if the previous value was 30 or lower, which means the cow can in fact reach that point in the specified time, we still need to check another point, which is 0, 0, because this is the point it will move off to from the grazing to the alibi. We will use the same procedure, and if the distance is less than or equal to the time difference, then we can finalize this cow committed the crime, just like what we did for the other point. And if it's greater, then it couldn't have committed the crime. Okay, now let's go over implementation details. We are first going to sort the points it agrees by time, because this is the only order that the cow can travel to commit the crime, because there's no other order. If you cannot reach a point that is later in time that have an earlier time in the input. So for each cow's alibi, we're going to binary search for the greatest time in a gradient that is less than the point in the alibi, and we're to check that point using the procedure in the previous slide. and we are going to run another binary search for the least time that's greater than the time in the alibi. So we can check these points using some sort of binary search, or if you're using C++, std lower bound. So a true cool trick is that you can store these points in the format of time first and then x and y coordinates. That way, if you sort it, you don't actually have to use the custom comparator, which is quite cool. All right, so before checking these points, we mark the cal as suspicious. So we mark the cal as if it can commit the crime until we have checked that it is not able to reach one of those points within the time difference. So we mark the cal as innocent. Also, just like a really important side note, it's not recommended to use the built-in square root function in languages when checking the Euclidean distances. This is because floating points errors can occur, which is basically sometimes in your code, the last few decimals can cut off, and that makes that can sometimes make the difference between a wrong answer. So you're better off squaring the expression inside the square root and the difference in time. And finally, your type complexity should be O of G log G plus N log G. The G log G is from sorting the gardens by time, and the N log G is from for each cal you're going to binary search over all the points in the grazing to find the maximum time that's less and the least time that's more. And that's about it for this question. Are there any questions? Okay, I guess we will go to problem number 3.
All right. We back. So yeah, let's look at problem 3. This one was like the graph one. So like the moo route one, which is sort of like BFS, except there's time travel, and we all love time travel. So we got M vertices, M edges. We start at a position C and end at a position D, and then we start at a time R and end at a time S. So we basically are DFSing, but the graph is really complicated, and the edges mean different things, and the nodes mean different things at different times. So let's observe an edge. Oh yeah, another thing to note is that like you need an AI layover time because we got to be annoying and add more constraints to the problem. So we initially have an edge from CR to DS, and the way we go is we sort our edges by R, and then take the edge with the largest R each time we do a DFS. This essentially means that we're going to like the latest time we can, and then moving forward, because, well, let's say we have like a bunch of edges in our graph that all radiate from a certain node, then the one with the largest R is going to be the one that we leave the latest, and our answer is supposed to be, I think, the earliest time that Bessie can get to airport I. See that if we start from the latest and basically just move our way forward, we can basically just go through all of the edges in like, we will never want to go through any of the edges we've already visited before. If we started at like an earlier edge, we would say, hey, why don't we go visit like this later edge over here, and then, well, we have a later edge that we haven't seen before. Let's just go visit that as well. This is going to basically make our graph much more complicated because we see that we will have a lot of times that we can visit this node, and we will essentially be covering the same edge multiple times with each traversal, with no idea on when to go and when not to go through each edge. Because if we just set like visited like in a normal DFS, because this would not work, because there is a possibility that there is a way of like entering the edge from like an earlier from like a smaller r into like a bigger r that we would not have accounted for otherwise. So the best way we would do this is essentially by providing some order into the edges that we have gone, some order into the edges that we are visiting, and basically take the edge with the largest start time and just remove the edge entirely from the graph. This ensures that we will never have like any confusion on whether or not we should go to the edge again. The answer is pretty much always no, because we're basically taking out each of the later edges and trying to move them into the earlier edges. So like our TLDR here is that this is basically a DFS. The only difference being that we sort our edges and then remove them without the inclusion of a visited array, but rather instead a priority queue. Or not necessarily a priority queue, just like sorting our edges and then removing the largest one each time. So we have I made some pseudocode because I got bored. So we have initially we want to set like the answer at airport 1, which is our starting airport, to 0, obviously. And then we would want to like DFS from starting from 1 with, I know that the start time they say is 0, but like it would be very complicated to factor in the layover, ignoring the layover times if we were to set the initial location to 0, because then we have to like basically check whether it's an initial location, and that would add like a bunch of lines to our code, and there's nothing that I hate more than extra lines in my code. So we basically, the best way to do this is to start this at -infinity so that we can just ignore all the layover stuff, and it's not going to cause any more issues because all the time steps are positive anyways. So while we have edges left, then we want to check if our current start time of this edge. So this basically takes out an edge like CRDS, or where C becomes V, and then I think I just used like RDS as it is. So we want to check if R, which is our enter time, is late enough that we don't like that we don't accidentally hit like break the layover rule. Otherwise we break. We can take out an edge with the largest R, as in literally remove it, and then update the answer for D to be equal to S, and then just basically run DFS from the edge DS. I also forgot the answer should initially be set to a list of all infinities, but that kind of goes without saying, and this is basically a min operation, but this also goes sort of without saying. So yeah, just running DFS over, we basically just run DFS over and over again and just check whether or not we can possibly enter at a latest time. And by sorting, we essentially preserve an order that, well, we know that if we were to visit like V multiple times, we would end up with like at the same position in the graph. So we find a way to capture all our answers while only visiting each edge once. So yeah, that's basically how we end up solving the problem. Any questions? No questions, then cool. I will be passing it on to, is there a next person?
I think that's it. Okay. Thank you guys so much for attending this workshop, and a special thank you to all instructors for taking a chunk out of the day to come teach. So yeah, if you like these kinds of explanations, you should check out joincpi.org/classes, where we teach Quantum server classes very similar to this. But yeah, other than that, thank you for coming, and we'll catch you next time.